All right. So here we have the equation for Markov. And let me choose a particular value of c. We're going to make c equal the expectation. What this means is what's the probability that the random variable x is bigger than the expected value. In fact, let's change this. X equals k times the expected value. K here is a constant. 1, 2, 3, 4, 1.5, whatever you like. Some positive number. So here, k greater than 0. Okay, so let's rewrite this. This says that the probability of x being greater than or equal to k times e of x. So I'm just plugging in k e of x for c is less than or equal to e of x over k e of x. That's just plugging in the value for c. And this equals 1 over k. Get that on my cam. All right. Take a look at it. Maybe this will make things click for why the Markov inequality is saying something. Let's make k equal to 2. This is asking the question, what is the probability that the random variable, when you push the button and a number appears, that this number is going to be at least 2 times bigger than the expectation? Markov tells us that the probability of that happening is less than or equal to 1/2. You cannot stray from the expectation by 2 times. You can't go 2 times away from the expectation with a probability of 2/3, say. Can't happen. Because if you could stray from the expectation 2 times with a probability of 2/3, then that means that numbers prefer areas that are larger than the expectation, which means that the expectation was calculated incorrectly. Let's make k equal to 100. What's the probability that you're 100 away from the expectation? Markov tells us that that is no more than 1%. What if it were more? What if it were 50%? What if with a 50% probability, numbers are appearing 50% of the time, 100 times away from the expected value? Then it means that the expected value is not expected. Like, because there's all of these numbers that are appearing 100 times away from the expectation. So if you're seeing all of these numbers really, really, really far away, then can the expectation be sitting here? No, because all of these numbers are really far away, like 100 times as far away. So the expectation should like move closer. There we go. To all of those numbers. All right. So assuming that the expectation is correct and it's not a guessing game, there's a formula, a definition for the expectation, then the expectation has a meaning given by its definition. And the meaning of the expectation is that on average, that's the number. If you do this process over and over and over and over and over, it's the number that would tend to appear if you average up all of the results. So that is what Markov is saying. Let me pick out Raymond.
Hello.
Hey. Does this idea of Markov's inequality make sense to you?
Yeah.
Okay, can you just explain it in your own words quickly?
I mean, like, I get what you're saying, but it's hard to say it a different way.
Say whatever way you like. Doesn't matter.
I'd say if you're gonna multiply the expectation by a certain number, then the probability of that cannot exceed 1 over the number you're multiplying it by.
Okay, perfectly well stated. Yeah, very good. Can you give an example? Maybe, I don't know, throwing a die. How about that? The expectation is 3.5 for a fair die.
All right.
How might you use this? Like, what's the probability of you getting bigger than 3.5?
Bigger than that, it'd be 2 out of 6. And then that can't be no bigger than 1/2. I get what you're saying. I'm just a little confused with the numbers.
Yeah. So, okay, really quickly, the first time I introduced Markov, understand Markov is not a very useful thing. Let's do this really quick. Raymond, stay with me. For a fair die, the expectation of a fair die roll is 3.5. Do you agree?
Yeah.
Okay, why is it 3.5?
Well, it's like the average. If you add them all up and then divide them by 6, that's what you're going to get.
Very good. Okay. Now, let's ponder what is the probability that you can be 2 times the expected value? What is 2 times the expected value of a fair die roll?
7, right?
7, perfect. Yep, you're right on. Now,
well, the probability of that is 0.
True, yes, true. Now you're realizing a little bit of a problem with Markov. Markov is correct, but not always useful.
Okay.
Let's say, so in this case, we're making k in the blue, in the equation, we're making k equal to 2. What Markov is saying is that the probability that on a fair die roll, you're 2 times away from the expectation is less than or equal to a half. Do you see that?
Yeah. Yeah.
All right. Do you agree with that?
Yeah. It makes sense.
Yeah. Is 0 less than a half?
Yeah.
It
That's
is.
kind of like stating the obvious.
Yeah, yeah. In this case, yeah, exactly. It's stating the obvious. So Markov is stating something that's kind of obvious. It's not exactly useful in practice. In fact, in practice, the way that Markov is useful is to derive other, more accurate bounds. But Markov is true. Like, it's true. And it's a good first pass. I mean, yeah, what's the probability that you like k times away from the expectation is 1 over k. And you can trust it. It's not necessarily useful, but it's true, and you can say that much. Okay. Thank you, Raymond. Okay, so this is Markov. Maybe here in blue is a more useful way of framing Markov. The above in black is the way that Markov's inequality is usually presented. But I think that the thing in blue is more intuitive. Think about it. Come up with your own example, play with it, and the important part about the thing in blue is that you're imagining what is the likelihood that the random variable is going to be close to the expected value. And that's the important thing about a measure of concentration. I'll go back up here again to these pictures. On the left, the random variable loves its expected value. Many of the values that come from the random variable are very close to the expected value. On the right, things are very spread out. Numbers can vary wildly from the expected value, and that's fine. That's just the nature of this random variable. So the idea of a measure of concentration is trying to come up with a measure for how close randomly generated values of the random variable are close to the average versus far away from the average. It depends on the random variable, but we can measure it. That's the measure of concentration. So with Markov in blue, again, this is putting into terms of the expected value. What's the probability that something is going to be far from the expected value or close to the expected value? There is a limit. If there's an expected value, then the probability that something is really far away is bounded by Markov. If you want to be 100 times away from the expected value, then the probability is at most 1 over 100. Not to say that it can't happen, it could happen, But the further and further and further away you go from the expected value, the smaller and smaller and smaller the probability becomes. All right. So Markov does this by relating probability to just the expected value, and that's it. Another nice thing about Markov is it works with any random variable, any one you like. Markov is always true. Similarly, Chebyshev is also always true. Markov, Chebyshev, the Russians have had a long time of being outrageously inventive with math. So props to them. Markov, Chebyshev. In the screen in front of you is Chebyshev. Chebyshev is what's called a tighter bound than Markov. Markov doesn't lie to you, ever. But, as we've said, be it flipping a coin, you flip a coin 10 times, what's the probability of 11 heads? You know it's 0. Markov tells you it's less than or equal to, less than a half, which is true. The actual probability is 0. Markov didn't lie, but it's not particularly useful. Similarly, when we talked about rolling a fair die, and what's the probability that you'll roll a 7? Markov tells you that the probability of that happening is less than a half. It is less than a half. That is true. That also happens to be 0. Great. So, Chebyshev is another measure to predict how far away from the expectation you could be. But Chebyshev is a tighter bound, where Markov might tell you that the probability of rolling a 7 is less than a half. Chebyshev, for example, might tell you it's less than 1 over 20, which is still true. It's a better truth than less than a half, because less than 1/20th is closer to 0 than 1/2. So this is what's meant by a tighter bound. It means that everything remains true. It's just that you're narrowing down the values. Okay, so it's true, the probability of rolling a 7 on a fair-sided die is less than a half. It's kind of more true that the probability of rolling a 7 is less than a 20th. And so the thing that gives us it's less than 1 over 20 is better than the thing that tells us it's less than a half. Really, the probability is 0. For this example, we know that. But this is what's meant by Chebyshev being a tighter bound. All right. Let's look at these things on the left and the right. On the left, what this says: the absolute value of x minus its expectation. This part. No, that part. This is saying the distance from the expected value. So if x is 7 and e of x is 3.5, then what's the probability that a distance of greater than 3.5 is going to happen? This is just, there's the expected value. X minus that is something. If you take the absolute value, then you're allowing that to go to the left or to the right of the expected value. And the probability that you're larger than C means if C is 1, what's the probability you're 1 away from the expected value? If C is 2, what's the probability that you're 2 away from the expected value? If C is 3, what's the probability that you're 3 away from the expected value? So this is the question that Chebyshev is asking. What's the probability that you lie so much to the left or to the right of the expected value? To the left or to the right doesn't matter, because there's an absolute value. It just means a distance from the absolute value. And the probability that you lie some distance, C, is bounded by the variance. Let me go back up to Markov. Markov relates probability on the left and expectation on the right. So there's an idea of probability, there's an idea of an average, and Markov marries these two ideas together. Chebyshev does the same thing, except it marries not probability with expectation, but probability with variance. And this is a tighter bound. Why is this a tighter bound? We could derive things, you could play with it, you can give yourself examples, which I suggest you do, because that's really what's going to make things click, is when you go through examples yourself. But the reason, on a high level, why Chebyshev gives a tighter concentration bound than Markov is because if we look at these pictures, Markov relates things to the vertical average line, and that's it, nothing else. Chebyshev measures concentration to the width, to the fatness of the random variable. So if you have a very thin random variable, like on the left, Chebyshev will notice the thinness of that curve. If it's really fat, then Chebyshev will notice that this is a very fat thing and take that into consideration, where Markov only looks at the straight line, up and down. So because a measure of concentration is very related to the variance, a big variance means fat, a small variance means thin. Then, if you're trying to measure how much things love the average, which is a measure of concentration, if it's concentrated, things love the average. If it's not concentrated, things can be away from the average in a not surprising way. So, Chebyshev relates the probability of lying away not from the average, but from the variance. And the variance is already a measure of thickness or fatness. So from a high level, this is why Chebyshev is a tighter bound. Again, tight here means both Markov and Chebyshev are true, always. But if you're looking for the number 0, the probability is 0, saying that it's less than probability of a half is true, but saying that it's less than the probability of 1 over 20 is more true. It's better. So neither of these are lying to you, but while Markov gives you a bound that's true but far away, Chebyshev brings that bound closer to the truth. You still don't know where in between, what it tells you and what the real value is. You just know that it's somewhere in that gap. Markov gives you a different gap that is still true, but it's a much wider gap. So Markov is nice, it's straightforward. Chebyshev pulls things closer. This is called a tighter bound on the probability. The bound meaning what is the thing that the real probability cannot exceed. If the real probability is 0, it cannot exceed 1/20th. It also cannot exceed a half, but saying that it can't exceed a 20th is better. That throws out all of these values in between that were nonsense to begin with. They're not lies. They're true. But when you're trying to find where the real value is, bringing the bound closer and closer and closer to where the truth values that you can play with are is the name of the game. Okay, so that is measures of concentration from a high level. Let's take an 8-minute break. Let's come back at 8. I will give one concrete, maybe two concrete examples of this, and I'll move on to the one thing I want to say about linear regression, and then anybody who has no questions can sign off. All right, let's come back at 8 o'clock. Think about the high level stuff. Markov, Chebyshev. Markov relates probability and expectation. Chebyshev relates probability and variance. Chebyshev is better. All right, leave it there. Hey guys, welcome back. So, do I have volunteers for, let's do Markov followed by Chebyshev. Markov is nicer. Come to the arena. You're welcome. I can be Caesar and just pick somebody that has a name I don't like. Or a name that I love. I don't want to say that I don't like anybody's name. Nobody. All right, Jake.
Yeah.
Welcome. Markov.
Okay.
We're just talking about it. What do you think?
Well, isn't it more reliable than I know less reliable than Chevy Chev.
Yep. Do you have a feeling for Markov? Like, does this make sense to you when you look at it? Are you confused?
Well, if we could say that it's less reliable,
Mhm.
I don't see the point in why do we use it at all? Like, what's the point of learning it?
Very good. Yeah. So unfortunately, basically the story goes Markov, Chebyshev, Hofting. Hofting is another inequality that is very, very, very tight. It's a very useful inequality. The problem with Hofting is that it relies on the independence of many random variables. Hofting takes random variables and adds them up, and then computes an average of the sum of lots of random variables. So Hofting, again, it only works with independent random variables. It's very tight. But it's also more complicated, and I thought about it. I'm not going to get into it this class. If there's somebody who likes these things, give me 20 minutes, and I will lay out Hofting for you. Hofting is really used many places, but a couple drawbacks. Number one, it's slightly more complicated, not too much, but it's a little bit more complicated. Two, and the big thing is that it only works with independent variables. Why am I bringing up Hofting? Is because you get to Hofting through Markov. So Markov's inequality, Jake, and this is a very, very good question, is by itself not particularly useful. But you can use Markov as an in-between step to other things. And these other things are really, really useful in certain circumstances. And you go through Markov to get there. So that's kind of why in the real world, anybody talks about Markov. For this class, the reason why I'm talking about Markov is not to get to the more complicated stuff, which is interesting. Like, I'd love to talk to you guys about it, but we have the summer to talk, so we can't get everywhere. But Markov also does capture this idea of a measure of concentration. That this idea of there's a random variable that it can be any particular value, but on average it's going to be this value. Given that a random value or that a random variable is going to be this value, then how much can you go around it? If you keep pushing the button, are you close all the time? Are you far away all the time? Markov is a way. It's not clearly not the best, but I mean it does capture this idea that you have an average random variable is going to appear around the average many, many times. On average, it's going to be around the average. On average, it won't be far away. It could be far away with a small probability. You can't say it doesn't happen. It does, but with a probability. So that's the thing on the left-hand side. Markov tells you no more could you have something going far away too often. If you want that to happen, it can only happen a certain number of times before something went wrong. Sorry, I don't know if that answers your question. So those are the two things. For this class, it's more of a conceptual thing that I want you guys to have this idea in your head. And although Markov isn't particularly useful, it's also not particularly complicated. And so this idea that there's an average and the probability of going really far away from the average is small. And this is like a concrete thing for that. The
Does
other
it
thing
deal
is,
with does this deal with the 30, 60, 90, or the 99.7 percentages that they teach in stats? I thought it was Chebyshev when you're talking about the concentration and how far away it is, and it goes from like 99.7 to 96.
very good. Yes, let me take 1 minute and I will talk to you about this. We have not talked about this in this class yet. What you are talking about are what's called a confidence interval.
Yeah, my bad.
No, yeah, not your bad. Thank you very much for bringing this up. You are correct. Chebyshev does come up here, and that's congrats. Like Chebyshev and this thing. Yeah, that's very good. That's it's exactly used here. Let me explain quickly in 1 minute. So, a confidence interval is when you're trying to make a model that makes predictions, which is what we're talking about in this class, by the way. That is what linear regression is. You are taking data, and from that data, you're making predictions. And you want to be confident in these predictions. Predictions, you're not an oracle, you're not perfect, but maybe the predictions that you make can be reliable. Reliable here is in relation to in the future, when you're measured against your predictions, how correct were you? So confidence is, what is it? I don't want to go down a rabbit hole. Let's see. All right. Probably approximately correct. All right. This is accuracy, confidence. I am sorry, guys. I'm trying to explain a concept to you. It's not too bad. I didn't sit down and think about it. Okay, a confidence interval. When people say, this is what will happen, I'm confident. How confident? I'm 95% confident that this thing is true. Or maybe I'm 50% confident. Like I can try to make a prediction and I can say I'm so and so confident in my prediction, which means my prediction could be wrong, but if I'm confident, on average, you should expect my prediction to be right. If I'm confident at 95%, that means that you listen to me 20 times, I will be incorrect once out of those 20 times. 95% of the time, my prediction is correct. So that is what's meant by confidence. There is a thing in machine learning. This is a paper that was written in 1984. Whatever. There's something called PAC learning, P-A-C. Probably approximately correct. This is not a machine learning course, but this, for me, made things click. What these concepts are. Approximately correct. This means that I'm trying to predict something, but I can't predict it exactly. Maybe I predict it with like a 90% accuracy. Okay? So 90% of the time I'm right, 10% of the time I'm wrong. That's the approximately correct. probably approximately correct is, so I'm right 90% of the time. How about this time? Am I going to be right this time? 90% of the time, I'm right, but my confidence on this time, me being 90% right, could be less or more. So I'm probably approximately correct. This is the same thing that shows up in polls and lots of things. Anytime you see confidence, they're talking about this probably part of the equation. So the idea when I was talking about averages of averages, and how the idea of taking not just an average, but an average of an average is like a really important conceptual leap to make. This is simpler. So there's a probability of a probability. There's a probability that I'm accurate, but there's also another probability that that accuracy is correct. And maybe this time it's not. Okay, that went over a minute, I'm sorry. But, okay, confidence interval in Chebyshev. So, we talked about a Gaussian curve. This has a mean of mu. That means that that's its average value. For a normal curve, this is about 0.36. The area of the curve is 1. All right? Now, Chebyshev. The area of this curve is 1, which means that, let's say, what's the probability? Good, Jake, you're still here. What's the probability that a value will end up here in this region?
50%.
50%. Very good. Exactly. Now, the area under this curve is 1, right?
Yes.
All right. So let's capture 95% of the area under the curve. I captured 50% just now. I want you to tell me how to capture 95% of the area. What do I do?
To capture 95% of it, starting at the medium point, which would be standard, like 0 standard deviations, you go 1 over, which is another 33.5 or something. And the third deviation, I think, is when you get to 95%. So there's going to be 5% left over. And it's broken up into like different quadrants or standard deviations because it gets smaller farther away from the median you get.
Very good. Yeah, so I can tell that you've taken some type of statistics class or something before. Some of the ways that you're using these words isn't quite right, but you are definitely on the right track.
All right.
So I want you to forget about standard deviations for a moment. Imagine the curve in front of you is a hill with a mass of 1. And what I want to do is to capture 0.95% of the mass. So if the mass is 100, I want 95 of it. How do I do that? Like, what's an easy way to do it? Like, forget about standard deviations and all this stuff. Yeah, like there's a hill, it's 1 or 100, and I want 0.95 or 95, whatever you like.
Take off 0.05.
Take off 0.05. Very good. All right, so 1 minus 0.5 is equal to 0.95. Sorry. 0.5. Great. Another thing, a hint, is that this hill is symmetrical. It is exactly the same on the left as the right, the shape.
Mm-hmm.
Great. So one way to get to this much, 0.95%, would be to take away 0.5%. So I can capture 95%, or I can eliminate 5%. I don't know how you like thinking about it, but both are equal points of view.
Yeah.
Let me lead you a little. Here.
Wait, what was the question?
Oh, I'm sorry. What is the question? How can I capture 95% of the hill of this? This is in area 1. I want 95% of the area.
Oh, does it involve taking 0.025 away on both tails? Like the highest percent, the lowest? I don't know how to. I think this analogy's kind of messed me up. I don't know what to do with a mountain.
Oh, I'm so sorry. That was not my intention. I'm sorry. Also, I turned off my computer while I was drawing. You can stay with me. What's happening? I'm sorry, guys. My screen is black. I'm trying to get it back. Okay. Here we are. Perfect. All right. Yes. So, Jake, you're saying that we can take this area, which is 90. Oh, no. Sorry, just turn off my screen again. Fine. This area, which is 95%. And to the left, we have 2.5%. And to the right, we have 2.5%. Yes?
Yes.
Great. Perfect. So this is a way to capture 95% of a probability. What this means is that you have a 95% confidence interval that your prediction, which is going to be mu here, is correct, or at least the range that you give. So in a poll, this person is winning 30%. This is the 30%, plus or minus 3. The plus or minus, like that would be 3 plus 3. This would be minus 3.
Yeah.
The person is winning this election, this percent plus or minus blah, and with some small probability, meaning less than 5%, that interval is correct. So they're accurate, plus or minus, with some probability. And Chebyshev does give you this. Chebyshev here, the probability that you're so far away from the expectation is smaller than some number. Here, you're looking for the number, here, 0.025. This, 2.5%. So, for this to be true, for you to be so confident, that means that you have an estimate on the variance and the expectation such that you can be so confident. This is what would give you the 2.5% confidence. The expectation is your prediction. The difference between your prediction, x, and the expected thing, e of x, is this region. Here's e of x, that's mu, and the absolute value of x minus that is this region here. So you want this region to be less than 95, less than or equal to 95%. Here, the probability is that region, and you want it to be less than 95%. So there's some type of expectation, there's some type of variance for this to be true. If you have such a random variable, then you can make these types of statements. Boy. Does that make sense?
Yes.
Okay. So, I'm sorry, it's really, I think I said 1 minute. It's way longer than 1 minute. Yeah, Chebyshev is a very, very good observation. I'm happy that you made it with this idea of sigmas being so many standard deviations away. By the way, with this whole thing, this region here, 95%, is what's captured in 3 standard deviations. 3 standard deviations in a Gaussian curve absorbs 95% of the mass. Why 3 standard deviations? Well, a standard deviation is the square root of the variance. So 3 standard deviations would be 9 times the variance, and you can work out with this. I mean, here you make the expectation of x equal to 0. You can make the variance equal to 1, and figure out like what the variance needs to be to make this be 95%. You take the square root of it, and you get something sort of up here, I guess, for the variance. But if you take 3 times that, you end up to exactly these regions. Okay. Sorry. This is not that deep of a class. This is where you can go in some of these things. Jake, very good job of making the connection between Chebyshev and confidence. I was going to talk about confidence and this type of thing on Thursday, but this is a good place to start. So, okay. It is 8:25. Let's take a 10-minute break. Sorry, I know it's a short break, but if we can, maybe we can wrap up earlier tonight. Because I have one more thing that I want to talk about. We're done with measures of concentration. After this, I want to talk about, from a high level, linear regression and why it's more powerful than you might think. And that's it. So let's come back at 8:35. See you then.